to get going. But a few latecomers following the exam. Let me hand the exams back. I'd like to go through them. I won't spend tons of time, but I'd like to go through the exam writers and all.
Good morning.
It was
Oh, yeah, like that.
yeah.
Sorry, I'll do pencil next time.
Okay, let me read through the multiple choice. We'll go through the short answers. The grade distribution is up. That's pretty solid start. I don't, obviously after an exam, some of you will be deliriously delighted. Others may not be. For those that are down towards the right there, two things. I know this won't make you feel necessarily better, maybe, but generally speaking, that grade distribution starts shifting to the left as we go through the class for a couple of reasons. One is I think students tend to get used to the type of exam that I set. Certainly the final grade distribution shifts to the left because of the thermodiagramming, the take-home exercise. As long as you do that and you take your time with that, that should help. But almost 20% A's, so 40% A's and B's, some in the middle, some on the right. I can't remember what the average was. Did I know the average? 76. Okay. All right. And we had a 98.3. I won't tell you who it was. I may do that. That was really good. Okay, so let me read through. 50% of the atmosphere lies within about 5 kilometers. That's C. Typically, water vapor occupies less than 2%. The average sea level pressure is 1013. C. Which of the following elements always decreases? It's pressure. It's D. The weather sphere is the troposphere. B. All of the following types of electromagnetic radiation have wavelengths longer than visible light, except ultraviolet. To the left, shorter one. That's D. The Earth emits terrestrial long-wave radiation all the time. Okay, that type of question was an application of radiation rule number 1. Anything above absolute zero emits radiation. This is another application of radiation rule number 3. If the average temperature of the sun increased, its wavelength of peak solar emission would shift to a shorter wave. Hotter the object, the shorter wave. Okay, this one got a few of you. Suppose last night was clear and calm. Tonight, clouds will be present. From this, you would conclude that the minimum temperature would most likely be higher than last night's temperature because the clouds have absorbed more of the infrared radiation and emitted down towards the surface. An increase in albedo would generally be accompanied by a decrease in radiative equilibrium temperature, more reflection. The annual combined albedo of the Earth and the atmosphere is about 30%. Examination of the global radiation budget suggests that the surplus of energy in the tropics gets falls. This one got a couple of which of the following latitudes, below we experience the fewest hours of daylight on December the 22nd? So that's in our winter. So the further north you go, the fewer the daylight hours. So that's 60 degrees north, which is D. According to Bion's displacement law, which emits the shortest wavelengths, just look for the hottest object there. It's the sun. The primary cause of the Earth's seasons is the inclination of the rotation of the axis, tilt of the Earth. E. On the global scale, the most important mechanism is latent heat. We talked about that in the energy balance. So that's B. This one got your head scratching a little bit. The good source region for an air mass would be B, generally flat areas of uniform composition of high surface winds. You want an air mass to sit over a region for as long as possible to take on temperature and moisture characteristics. A warm, moist air mass that forms over water is called maritime tropical, and C, compared to maritime polar, maritime tropical, warmer and moist. B. Okay, here's the electromagnetic spectrum, right off the slide. Carbon dioxide is down as far right as you can, so that's E. CO2 will emit radiation emitted by the Earth. The flip side of that is 21, which is A. Ozone, predominantly ultraviolet, left of the visible spectrum. 22, visible light occurs in B, right in the peak. The air is saturated, which of the following statements is not correct. An increase in temperature causes condensation to occur. It's not correct. 24, you had more information than you needed. You just needed to divide 12 millibars by 25 millibars to get 50% relative humidity. Cooling the ground to produce dew is mainly the result of radiational cooling. Did that little diagram plot, so that's P. The force that causes a stationary parcel of air to move horizontally is the pressure gradient force, D. Which statement below is not correct? It's reflected to the left in the northern. So that's D, and the answer is correct. Which of the following is the greatest change in pressure? Anything good inverting balloon ascent from sea level to 5 miles, you get 50%. 29, the most common way for air to be cooled is rising and expanding, so that's B. 30 is C. We add 10 millibars every time. Most of you circled B on the diagram, but some of you were, and some even put yippies on there. So, okay, short answers. Most abundant gases: oxygen and nitrogen. Oxygen at 21%, nitrogen at 78%. I was really quite pleased with 2. You did really well on 2. Okay, the diagram shows the Earth's emission curve. What's the significance of the shaded areas, the light brown? That's absorption of long-wave radiation by the atmosphere. It causes global temperatures to rise. Why does this happen? It happens because of radiation law number 2. Certain gases absorb at certain wavelengths. Why is the entire area not curved? Because some gases let long-wave radiation through. If the entire area was shaded, we would increase our temperatures to an unlivable level. What happens between 8 and 15? That's the atmospheric window where radiation escapes to outer space. So pretty good there. What does continentality mean? Large-scale variations in temperature relative to proximity for water. Meaning and significance. Q, you got the whole thing correct. So Q is incoming radiation, little q is diffuse, 1 minus alpha. That's the percentage of the incoming radiation that's absorbed. Alpha is the albedo, long waves going out, long waves coming back. The significance of the terms is that it allows you to calculate whether a surface is increasing temperature or decreasing. There's the SVP curve. As promised, approximate dew point of a parcel of B, mid-40s. I took anything around 43, 44, 45 Fahrenheit. It's good. Relative humidity of B, I was looking for something right at around about 60, but I gave you a reasonably wide range, 50 to 65-ish, something like that, right? That was 10 millibars divided by, and you go up to the line, and that could be 15, 16, or 17. And which parcel is closer to saturation? That's A, closer to the line. Which of the 3 parcels has the highest water vapor content? That's C. Notice the question was A, B, or C. Parcel D is in an unrealistic position, playing Y. And that we went through in class is the 90% temperature, 90% relative humidity. Because if you cool it to a dew point that has a dew point of 100 degrees Fahrenheit, you'd be rewriting the textbooks at that point. Station model map on the next page. Would you describe the atmosphere as humid or dry? So clearly humid. All I needed to see there was temperatures and dew points are very close to one another. Winds are out the south. Most of the lines there indicate various thicknesses of fog. I didn't take off points if you didn't mention fog because I didn't ask you to remember those symbols, but you just needed to look at them if they're indeed one thing. Infrared satellite image of the US with the low pressure system. This was directly taken from the slides in class. Why do we look at infrared satellite image? For benefits. So infrared satellite images tell you the temperature of the clouds. They can tell you the low warm clouds versus the cold high clouds. Plus the other benefits that you can operate in 7. latent heat, what is meant, it's the phase change. The release of heat as water changes from liquid water back into water vapor, and it's important in the energy balance because it transfers heat out of the ocean into the atmosphere. So that's important in making the which that happens, something along those lines. Okay, map below, I took this from last Thursday. It's an upper level surface chart, so it's an upper level chart. You just have to look at, first of all, the numbers 579, 540, there's 5400 meter contour, so it's clearly a 500 millibar chart. And you can see the wind barbs are parallel to the isobar, so it's geostrophic flow. Is meridional, it's a meridional or zonal. It's clearly zonal, moving from west to east. We don't see any ridges or troughs across the middle part of the United States. The bonus question: why does the jet stream generally occur at about 300 millibars and not at the top of the atmosphere where friction is at a minimum? That's where, because of the pressure gradient is steep. It's a full column of warm air, short column of cold air, and then those pressure gradients reverse above the cold air over the polar regions. And number one is in the books. Thoughts? What you expected? Worse or better? About what you expected? If you haven't done as well as you hoped, then please do come and chat. And I would be happy to, let's see if this is working, to go through it again. The other thing, of course, that I'll throw out there is I'm more than happy to work with you individually as you go through the semester. Some of you have already taken advantage of that. But again, if you haven't done as well as you'd hoped, I know it's easy for me to say don't panic, but don't, right? Take it head on and figure out how you can shift that. I'll pick up the exams at the end. You'll all do. Okay. Yeah, they were all worth 1, so it's 30. The short answers were worth 30, so it'll basically balanced. And it's yeah, I think it's going to be very similar for 2 and 3. Maybe there'll be a few less multiple choice on 2 and 3 and more of the written. Okay, cool. All right. Moving on, big section here. There are basically 3 components to this, and this is really the last of the fundamentals, and this is really important as it relates to your thermodiagram take-home exercise. Okay, so the 3 components are stability, which we will probably only get to today. The next, and so stability all focuses on a simple question. Will air rise or sink? That's it. Okay? So we've got to deal with that. And then we've got to deal with clouds and then precipitation. So cloud classification, and then how do we actually get any kind of precipitation at the ground, right? So we're moving deeper and deeper into that saturation vapor pressure curve where you've got to get a parcel of air onto the saturation vapor pressure curve, got to bring it to its dew point. You've got to continue to lift it because then it slides down the saturation vapor pressure curve and you start seeing clouds. And then you've got to do a bunch of other things to it where you get rainfall. Okay, so that's where we're at. So let's talk about stability. And what we're going to do here this morning is you're going to see a lot of X and Y plots. Okay, but it truly is important that you understand this concept. You're going to apply it in, as I say, in the building. Okay. So the starting point occurs twice a day, at midday and midnight around the world. In the US, at midday and at midnight, the National Weather Service releases these weather balloons, balloon filled with helium. And attached to the bottom is one of these little transmitters, okay, a data pack that you can see up on the right there. It's got a return to sender address on it because they do fall back to Earth. And in that little transponder are the instruments that will measure temperature, dew point, pressure, and so on, right? So this is a little mini weather station that's released at midday and at midnight that sends the data back to the National Weather Service. We release, or they release 92 of these at each time point. So midday 92, midnight 92 go out. Pretty good geographic distribution. There's about 1,800 that go up across the planet from all the weather services. And they take the data that comes back is plotted in what we call an atmospheric sounding or a vertical sounding. So we're taking the pulse, if you like, of the atmosphere as you go up vertically. Obviously, there are large areas that are not covered. You can see those over the ocean surfaces and some of the high latitudes, right? But that's where we get the data to begin to understand the upper levels of the atmosphere. Okay. Funky little slides. So if we look at the atmosphere from a very broad perspective, okay, so we take a step back and let's say we're looking at the atmosphere across the entire United States. The question is that atmosphere conducive to air going up or air going down, right? In a very simple level. So in a low pressure, air goes what? Up, right? And in a high pressure, air sinks, it goes down. So if you want to bring an air parcel to saturation, if you want to get it onto the SVP curve, if you want to get cloud development, storms, convergence, all that stuff, you've got to get air to go up, right? You've got to have an atmosphere that is conducive to air rising vertically, okay? Does that make sense? Okay? If the opposite is true, then the air is sinking and it's warming by compression and you're moving away from the saturation vapor pressure curve. That's great if you want nice calm weather, right? But if you're interested in storms, rainfall, anything like that, you've got to get air to go up. So that's the first point. Second point is, when you look at the atmosphere, again, over a large region, right? So this one here, let's just go to the top right. This shows an infrared image of a very large mid-latitude storm system. We're still going to look at mid-latitude storm systems, but there's a big low pressure there, right? A huge cold front here. It's the kind of system that's just impacted the Northeast. When they occur off the East Coast, they're called nor'easters, right? And that's what dumped all the snow on New York and Massachusetts and so forth. And you look at that and you see all this vertical clouds and you look at how high and white those clouds are. They must be very high. They must be very deep. There's this notion that the atmosphere is letting the air go up super rapidly, right? So when I say we're looking for an atmosphere that is conducive to air rising, that's what most people think of. They just think of, vertical air rushing. And that's actually not the case, okay? That's not the case. When we talk about an atmosphere that's conducive to air going up, those rising currents and motions are incredibly gentle, oddly, okay? So here's why, and this is what's going to look a little strange, so bear with me. Let's look at the left here. So on the left, okay, is an image that is relevant to the one on the right, okay? And the scale here, the color key, is vertical velocity in MBS, millibars per second, right? Okay, vertical velocity in millibars per second. Okay, the values are taken at 700 millibars. That's the mandatory pressure level. If you were to have a guess, what height do you think that occurs? Can you remember? 700 millibars. This is a guess in kilometers. Say again? 3 kilometers. Right? Right at about 3 kilometers. Good. So 1,000 millibars is the surface. 850 is at about the lifting condensation level at 1.5 kilometers. We look at 700 because it's at that 3 kilometer level. Nice. And that's kind of in the guts of any kind of storm development. Right? If your lifting condensation level is at 1.5 kilometers, another 1.5 kilometers, you're in the storm. Okay. You go to 500 millibars, you're in the upper levels now. Does that make sense? So 700 millibars is an incredibly important mandatory level to look at whether air is going up or down. Okay. So this is a 700 millibar vertical velocity in millibars per second. The wacky part of this is the scale. And that is, look at just how small these values are, 0.001, 2, 3, 4. And the dark purples, right? These big blobs here, okay, which correspond to the storm system and the cloud development, are very, very small millibars per second, 0.004. And the other wacky component, which may seem odd at first, is that the negative values represent air going up. Bizarre, right? You would think that velocity would be a positive value as it's going up. But in meteorology, vertical sounding, vertical velocity are negative values. Why? Because pressure decreases with height. That's why. Okay. So the bottom line to this map on the left is, as you're looking at the blues and the deeper purples and the even deeper purples and the magentas down here, that's showing air going up, and the yellows and the reds show air that is sinking. Does that make sense, everybody? Okay. And then let's just do a very simple calculation here, and I've got this written out on the screen as well, on just how gentle these upper winds are. Let's say we're right here in the heart of these storms, in the very, very deep purple at 0.004. Okay, and it turns out that the pressure in the center of this low pressure center here was 955.2 millibars. It's pretty darn low, right? So 955 millibars, you'll see later on when we get to hurricanes, that you would find that in a hurricane easily. Okay, so this is a very strong, deep, low pressure center, 955.2 millibars. Okay. And the maximum vertical velocities here in millibars per second is down here in the purple, 0.004 millibars per second, right? Showing the fastest upper moving winds. So how fast are those winds blowing? So there's an easy way to determine that, right? The easy way to determine that is, let's look at 850 millibars. So we'll go to the lifting condensation level, assuming that the LCL is at 850 millibars. And then let's go to 700 millibars, right? And we assume that we've got nice big full clouds here, okay? So that's 150 millibar difference between the lifting condensation level and your 3 kilometers, right? So we're looking at the base of the clouds to the inner workings of the storm, okay? So over 150 millibars, if we take that and we divide that by the vertical velocity of 0.004 millibars per second, so 150 millibars divided by 0.004 millibars per second, the millibars cancel out. And what that ends up with is 37,500 seconds, okay? Or 10.5 hours for the air to go from 1.5 kilometers to 3 kilometers. I mean, we're not exactly breaking speeding records here, right? Does that sort of make sense? So again, take a step back. When we talk about how stable or unstable or volatile the atmosphere is over large areas like this, we're talking very, very gentle upward movements like that, okay? That may take, half a day to go through 1.5 kilometers. I mean, talk about a tortoise. But that is totally different from this. That's completely different to looking at the vertical velocities inside a very specific storm, okay, over very small scales, right? Because we know when you see a thunderstorm developing, if it's we'll get to exactly what unstable means, but if it's a very volatile atmosphere, you can see storms billowing and developing, right? And you can see those clouds lifting up through thousands of feet in 10, 15, 20 minutes, okay? Clearly, the vertical velocities are going up much more quickly. Or if you fly through a storm in a plane, the turbulence is not going at the speed of 10.5 hours to go up 1.5 kilometers. That's going to do nothing. You would never even feel that, okay? So we've got, and I'll go back a second here, we've got very gentle overall conditions across a large area. Is it conducive to gentle rising and gentle falling? And then we slap a cold front in, or something happens that gets air to go up very quickly in the storm system. That's totally different. Okay, so I just wanted to kind of frame it as that before we get to the details of stability and instability. All good.
Where'd you get 850 millibars from?
That's just me saying, let's look at 850 millibars as where the base of the storm is.
Yeah.
Yeah, that's a
And
good
you were
question.
saying that it takes to go from 850 millibars to 700, that's 10.5.
Exactly. And 850 millibars is generally at about 1.5 kilometers.
Yeah.
And 700 would be generally at about 3 kilometers. So I mean, it's 1,500 meters. Okay, think of that 3.5 times around an athletic track. That'll take you 10.5 hours. Okay, maybe my overweight dog would take that long, but I mean, we're talking it takes a while, right? Does that make sense, Andrew? It's a good question. Yeah. Okay. But again, you may have an overall atmosphere that's conducive to air rising. The question is, what's going to happen in specific areas in terms of the storm? Okay. So that's where we start unpacking this whole stability. All right. We are underway in stability. So as we start talking about stability and instability in the atmosphere, we're going to spend the rest of the morning, and you're going to do this when you do your take-home exercise. We're going to talk about parcels of air, balloons of air, or bubbles of air. Okay, that may seem odd, right? Because the atmosphere is fluid and it's dynamic and it's moving. That's the only way we can handle it. Because actually, if you heat an area, let's say it's the sun comes up and it's a warm morning, and we've got these huge grassy areas, but right in the middle is an asphalt parking lot, right? That's going to heat up more quickly than the grass. Okay, and the air above that parking lot is going to heat up more quickly. So we do get these areas of pockets that heat up and cool down. But to understand stability and to do the calculations, we have to think of little balloons, bubbles, or parcels, right? It's called parcel theory in meteorology. So I'm not just making stuff up. This is how we do it. We look at parcels. Okay, let's think of this. Let's say we've got an island. I have no idea which one this is, but it looks rather pleasant. And it's sitting out in the ocean, right? Somewhere. And the sun comes up and we start absorbing radiation. Now, you probably would be able to argue pretty sensibly that the air above the island is going to be warmer relative to the surrounding ocean, right? So that island is going to heat up more quickly, and solid areas will heat up relative to forests and water and so on. But all things being equal, this is going to heat up as the day wears on. And the air above that island is going to be warmer relative to the cooler surface. Right? What happens to the air above the island as it starts warming? It becomes, in terms of density, as it warms. It becomes what?
Less dense.
Less dense. Yeah, so we've got, just think of a balloon sitting above this island. And that island starts warming up, and then that heat starts moving into the lower parts of the atmosphere by conduction and starts heating it. And then that air, as you heat it, it becomes less dense. Right? So what happens to the air as you heat it and it becomes less dense? It does what? It starts going up. And as it rises, it starts cooling, right? By expansion. We've already explained that. Okay. And as it gets higher, it keeps rising and it keeps cooling by expansion relative to the cooler air around it. Okay, does that make sense? Now, what's interesting, I think, is that just increasing the density of the bubble of air is actually not enough to cause that air to rise. Okay, what's Newton's first law of motion? Anyone remember it? The first law of motion is an object at rest will stay at rest unless acted upon by another force, right? You've got to have a force, good, and you've got to have a force to actually get the air to go up. If you can increase air density, that's awesome, but that's not a force. The air just becomes less dense as you warm it here above the island, right? What actually happens is as you increase the temperature and decrease the density of the air, right? So the air does become less dense and it warms up, okay? That doesn't just cause spontaneous rising. It's the colder air that is dragged down by gravity that actually acts as the counterbalancing force that forces that warm air to rise. That's exactly how a hot air balloon works. Okay, how do you get a hot air balloon to rise? Big floppy balloon, and you start pumping heat into it, right? So you turn the gas on, and that increases the temperature and reduces the density, and the cold air around it undercuts that and causes the air balloon to rise. Okay. What's key here? So try and keep this visual in mind as we talk about these graphs, because the graphs are dull. Sorry, just to be honest, they're just X and Y plots of temperature versus height. Try and keep this image in mind where as you increase the temperature, you're decreasing the density, and that cold air acts as the force, the buoyancy, right, in that air parcel causes that air to rise. And as it rises, it cools by expansion. And the key for this whole discussion of stability, okay, the bottom line to all of this is what are the temperature dynamics in the parcel relative to the surrounding environment? What's going on here in this parcel relative to the environment around that island? Okay, that's the key for determining stability. There's one other thing, and we've got to get it out of the way, and that is this term. And that term is adiabatic. Right, you're going to see that a lot in the next few minutes. So what does adiabatic mean? Adiabatic means that there is no energy exchange between the air parcel and the surrounding environment. Okay? In other words, as this air parcel goes from that size to larger, we're not adding any energy in the environment or taking energy out of the parcel. We're treating that parcel literally as a balloon with a skin around it that doesn't allow any heat exchange between it and the environment. May seem odd, but that's how it works. Okay? All right, all good.
The force that's making form or rise
Is what?
well, I just know it's less dense and then it rises, which makes it colder. But what's the point?
So yeah, so the let's assume all of that land use is exactly the same. Let's just say it's all dry grass or dry trees, right? That's going to heat up more quickly than the surrounding land, right? And that air is going to be less dense as you increase the temperature over that land, right? So it begins to rise. And most people just stop right there and they say, well, you warm the air, you increase the temperature, and you decrease the density, and it rises. But physically, the force is the cold air being dragged down by gravity, which then causes that less buoyant air to go up. Okay. All right. Don't worry about that 1 5 here. Okay, so here are the all exciting diagrams, right, that we're going to go through. So first of all, in all of these diagrams, we're going to plot Z against T, and the Z always stands for elevation, and the T is temperature. So all of these plots are elevation against temperature. Now, for those of you who've done stats or any kind of graphing, okay, this is the Y variable and this is the X variable, right? And when you're plotting a relationship, there's a dependent variable and an independent variable. Which is the dependent variable? Always the Y, right? The change in Y depends on how you change X. In meteorology, we actually flip that sideways, okay? Elevation does not depend upon temperature. Temperature depends upon elevation, right? We know that temperature goes down as you go up. It's just visually and computationally, but much more important visually. It makes sense to look at a diagram like this, and when this is height, as you go up, you're kind of visually going up as you move up that axis, right? So don't get bogged down and think, wait a second, it's actually plotting the Y on the wrong axis. Everybody does this. It's the way we look at it. So it's looking at how temperature changes with height in all of these plots, okay? So it's delta T over delta Z, the rate of change with temperature with height. And the change in temperature with height is known as a lapse rate. The change in temperature with height, okay? It's the change in temperature with height. So an adiabatic lapse rate is a change in temperature with height where you're not adding or taking away energy to that parcel. So that's the term you're going to see a lot here this morning. Adiabatic lapse rate, the change in temperature with height without any exchange of energy between the parcel and its surrounding environment. Fair. All right. So take these notes down. These are, and I'm going to ask you to remember these on the world's most boring slide. Okay. But really important. This is just one of those like 1013 millibars, 500 millibars. I'm going to ask you to remember these. You're going to need to. So we're going to deal with 3 different types of lapse rate here. Okay. One's the ELR, the environmental lapse rate, the ELR. And that is the actual change in temperature with height. That's the data we get back from the weather balloon, right? Okay, now don't worry, wait a minute, there's a balloon, it's a different kind of balloon. We're talking about individual parcels versus sending up a weather balloon with an instrument that's sending back the environmental lapse rate, the ELR. So that's the temperature change of the ambient air, okay? Right? And broadly speaking, when you look at the atmosphere, it's around about 6.5 degrees Celsius per kilometer, but that changes hour by hour by hour. So that's very much an average, right? 6.5 degrees Celsius per kilometer. We always work in Celsius and kilometers, even the National Weather Service, the Americans, finally. Because working in degrees Fahrenheit and feet, you're dealing with decimal places and it's a nightmare, right? So the temperature of the ambient air on an environmental lapse rate on average. So in other words, when I showed you that first diagram and I showed you elevation here and temperature, and remember we looked at the troposphere and then the stratosphere and the mesosphere and the thermosphere, that average line that you saw on that first diagram is the environmental lapse rate. And 6.5 degrees Celsius per kilometer. Cool. Second is the DALR, the dry adiabatic lapse rate. Okay, the dry adiabatic lapse rate is always 1 degree Celsius per 100 meters. It's always 10 degrees Celsius per kilometer. Okay, that is what dry air will cool at because of expansion into a decreasing pressure environment. So if your air parcel is dry, now we're going to start really building in these concepts here as we move through the morning, right? In other words, if this is vapor pressure and temperature, if your parcel plots anywhere here underneath the curve and is not saturated, and you start cooling it towards its dew point, it will cool at a set rate, 1 degrees per 100 meters, period. Does that make sense? Okay, that's the dry adiabatic lapse rate. And then there is the SALR, right? The SALR, or sometimes that's known as the moist adiabatic lapse rate, saturated or moist. And this is the rate at which an air parcel will cool when it hops onto the saturation vapor pressure curve here, where the relative humidity is 100%. Okay? It's the rate at which a saturated air parcel, and it is variable. It is not set. It's not set. But we do know it is less than the dry rate. So if the dry adiabatic lapse rate is 1 degree per 100 meters, the SALR is less than that. Okay. On average, it's about 0.6 degrees Celsius per 100 meters. On average. Okay. So how does that work? Well, it depends if you're dealing with, if we think back to that very first diagram when we did water in the atmosphere, and I had the atmosphere over Scotland and the atmosphere over Arizona. Remember that, right? Let's say this is the atmosphere over Scotland, parcel A, and parcel B here was the atmosphere over Arizona. Okay, that makes sense? Right? If both of those atmospheres were saturated, right? So here's the Arizona air sitting on the saturation vapor pressure curve, and here's the Scottish air sitting on the saturation vapor pressure curve. Which one has more moisture in it? the Arizona, right? It's got a much higher vapor content. Okay, this has a much lower vapor content. So the rate at which the saturated adiabatic lapse rate occurs depends on whether it's a lot of moisture in the parcel at saturation or not much moisture in the parcel at saturation, right? So if you're dealing with an air parcel that is way down here on the curve with very low vapor pressures at saturation, it's going to cool at a rate that is very close to the dry adiabatic lapse rate. It may be 0.95 degrees Celsius per 100 meters. It won't be 1, but it'll be close. If it's a drier parcel of air, right? If it's a very, very wet parcel of air, okay, if it's saturated over Arizona, or you're dealing with a very saturated parcel of air sitting in the middle of a hurricane, it's going to be much less. It's going to cool much less quickly. And the question is, why? And if you can answer that, you can pick up your notes and disappear for coffee for the morning. Not really, but why do you think the saturated, first of all, why is the saturated adiabatic lapse rate less than the dry? And why is it way less than the dry as you're getting wetter and wetter and wetter, more moisture in an atmosphere? Note this. What do you think? Think.
Amount of energy necessary to get it to cool.
Maybe, I mean, you bought a ticket to the ballpark. You're in the ballpark. And no. Dry parcel going to rise 1 degree per 100 meters. Saturated parcel will be either 0.98, 0.95, 0.97, 0.96, depending if you're dealing with dry air over Arizona that might be saturated, or saturated air over Hawaii in the Pacific that might be saturated. In other words, more moisture in it. Because when a saturated parcel of air is rising and cooling, in other words, let's say it's here and it continues to rise and it continues to cool, it stays on the SVP curve, right? What's going on as it stays on the SVP curve? It's condensing. And as it's condensing, it's doing what? Claire, keep going. Yes.
It cools more because
Yes. And it condenses more and it cools more and it condenses more. And what's happening as it's condensing into,
it rises.
and it keeps cooling and what's explaining the fact that it's suppressed the cooling rate? It's not cooling at 1 degree, it's cooling less quickly. Because whilst all that's going on,
It absorbs the energy from like the radiation of the sun and the water for the quicker, so if there's more water parcels coming out, it's gonna be.
yes, exactly. And what is that doing? What is it? It's releasing what?
Energy.
What kind of energy? What do we call it? Latent heat. Hey. Latent heat, right? Remember the energy staircase? Okay, if you're changing that liquid water into water vapor, you're adding 600 calories of energy. So you're right on track there, Claire. 600 calories of energy to your gram of water, your one little paltry gram of water. You've got to add 600 calories to get it into water vapor. When it condenses back into liquid water, it releases. Every gram releases back that 600 calories and starts warming the ambient air around that when it's all happening. So inside a thunderstorm, inside a cloud, as that water vapor is condensing back into liquid water, it's releasing huge amounts of latent heat. So all the way along this rise, all down here, is LE, latent heat, being released. And that slows down the rate dramatically. Okay. And if you're in a very wet environment, so now you're sitting in an air mass over Indonesia in the tropics, right? And as you said, it's absorbed all that energy to convert that into water vapor, and it releases vast amounts of heat, then that cooling rate is suppressed dramatically. That's what fuels hurricanes. Does that sort of make sense to everybody? Okay, so again, we've got three things. The ambient environment, just think sending up a weather balloon with a temp thermometer, that tells you what the environment is. How your air parcel will cool if it's dry, 1 degree per 100 meters, and what your air parcel will do if it's wet. Variable. 0.6 is a good enough one, because most of the time, the air is somewhere in that range, unless you're dealing with deserts, which are dry air conditions, obviously. Okay. All right. We're getting there. Okay. So how do we determine stability? Okay. Another important section here. Okay. So hang in there. If you're flagging, run to the bathroom and put your head under the faucet, because this becomes super important for your take-home exercise. So how do we determine stability? So what we do when we determine stability is we look at the environmental lapse rate, and then we look at our air parcel and how is it cooling relative to the environment. Okay. So in these diagrams, what you'll see is in blue here, and this is incredibly simple, right? We're just doing straight lines for the moment. In blue is the actual lapse rate. That's the environmental lapse rate in blue, the ELR. So that's what the weather balloon sends back. And it's showing you that your temperature is decreasing with height. Okay. And you start your parcel. So you go out onto the patio with your parcel here, and you say, okay, if I can lift my parcel, so pretend you've got this ladder that goes right up into the atmosphere. You hop onto the ladder and you tie your balloon to your ankle and you start climbing the ladder. It sounds stupid, but as you start climbing the ladder, right, that parcel is going to slowly expand and it's going to cool as you get higher and higher and higher, right? And you get to a certain elevation, whatever the elevation is. Let's say you get to 1,000 feet. So your Z is 1,000 feet. And you look at the temperature of the parcel relative to the temperature of the air around. And if those two temperatures are the same, and you cut the ribbon and you say to the parcel, okay, now you do whatever you need to do, the parcel will stay right there because its temperature is exactly the same as the ambient air around. Does that make sense? Okay. That's a neutral atmosphere. And that doesn't happen widely. It happens, but that's not the norm. Okay. So a neutral atmosphere is that the temperature inside the parcel is the same as the air temperature when you release it, when you take your hands off it. And graphically, the easy way to think of it is your dry adiabatic lapse rate just follows your environmental lapse rate. That's highly unlikely to happen as you go up the big atmosphere. It may happen in certain sections, but not throughout the deep atmosphere. Right? Okay. So a neutral atmosphere is the exception, not the rule. And that's where the temperature and the air parcel are the same. Okay. Here's where things get more interesting. Right? A stable atmosphere occurs when the temperature inside the air parcel is less than the temperature of the ambient air. So you get up to 1,000 feet on the ladder and they cut your string, okay? And the temperature inside that parcel is less. It's colder than the surrounding air. What will the parcel do? It will sink because it's colder and it's more dense, right? Bless you. So a parcel will return to its original position if it is stable, if its temperature is less than the surrounding air. So in this example, here's the environmental lapse rate in blue. So this is what the weather balloon sends back. Temperatures decreasing much more slowly, right? And you go to the surface and you say, okay, I'm going to take my parcel, I'm going to climb up the ladder, and I'm going to stop right here, take my hands off the parcel, and what does it do? Okay, its temperature, and this is what I want you to do. I'll use green here. It's what I want you to do, even in an exam. If you're getting confused, just draw it. Draw an X and Y, draw Z and T, go to a certain height. Let's say this is 1,000 feet right there. You go to 1,000 feet, compare the temperature So there's the temperature of the parcel at 1,000 feet, and there's the temperature of the air, or the temperature of the environment. Does everybody see that the temperature in the parcel is less than the temperature of the environment? Always do that. Go to the height, go across to the two lines. What's the temperature in my parcel? What's the temperature of the environment? And if it's colder, it will be stable. Okay? All good? And then the flip side of that is if the temperature in the parcel is greater than the temperature of the air, then you have an unstable environment. Okay? So this may be the environmental lapse rate here. Good. And you go to the surface and you start lifting your parcel along the dry adiabatic lapse rate. Everything assumes that that parcel is dry and not saturated. And you start lifting it, it starts expanding, it's cooling, it's getting closer and closer to its dew point, and you say, let's stop here and look at the temperature inside the parcel, which is this temperature, and the temperature in the environment, much colder. Take your hands off the parcel is much less dense, it's warmer, and it will continue to rise up along that dry adiabatic lapse rate. That's an unstable environment. Okay. So the two endpoints are stable. Any air parcel, you go outside and you give it an upward nudge, and it'll come back down, right? In a stable environment. In an unstable environment, if you give your parcel a nudge, you take your hands off, it'll keep going. And obviously that's what you want if you want storms developing. Because if your parcel wants to rise on its own, then it'll keep cooling and sliding towards the SVP curve, right? So an unstable environment is one that is conducive to vertical motions in the atmosphere. So when I was first taught this, back in God knows when, a long time ago, this was a diagram that I got used to, okay? And I remember my professor said, please don't learn this where if your environmental lapse rate lies to the left of the dry, it's unstable, and if your environmental lapse rate lies to the right of the dry, then it's stable. She wanted us to understand the physics behind it. In other words, take any height here, and compare the temperature in your parcel to the temperature of the environment. It's much warmer, therefore it's unstable. And here the temperature in your parcel is much colder than the environment. It'll be stable, right? But that's kind of a nice summary way of looking at it. All related to dry unsaturated. Okay. Any questions? Okay, good. All right, that's all dry. Okay. If your air is saturated, then you've got to ignore the dry adiabatic lapse rate. And you've got to compare your parcels with the saturated adiabatic, right? And the moist adiabatic lapse rate is not constant. That's the pain, right? So if we say the moist adiabatic lapse rate is 0.6 degrees per 100 meters, okay, that's going to change where you are vertically in an atmosphere. You may be near the surface, right? And you may have lots of moisture there, and your moist adiabatic lapse rate may be one number. You may be in the middle layers of the atmosphere where it's drier, and it's going to be a different number. It's all going to be less than 1 degrees per 100 meters, but it's not constant. So we take this average value. This just works well. And you're going to see, even in your take-home exercise, you're going to use the saturated adiabatic lapse rate at 6 degrees Celsius per kilometers, or 0.6 per 100 meters, right? So here is the dry adiabatic lapse rate, cooling at 1 degree, and this is what a saturated adiabatic lapse rate curve looks like. So on the thermodiagram that you'll get, and I get to go through that next week, okay, it's an easy distinction. Any straight line is a dry line. I shouldn't say dry line, that's a different thing. But any straight line is a dry adiabatic lapse rate, and the curved line is the saturated adiabatic lapse rate. Okay. And we'll just use the 0.6. Okay. And this is what the atmosphere really is most of the time. Most of the time, we talk about conditional instability. Okay. And the conditional instability is a really important concept because the stability of the atmosphere is conditional upon whether it is dry or saturated. That's what it comes down to, right? is your parcel already sitting on the saturation vapor pressure curve at this level or not? Okay, so where are you on the saturation vapor pressure curve? Are you there or are you there? That will determine the stability of the atmosphere. So I love this little diagram. It's slightly different from a different source. So here's altitude in kilometers and temperature. So we've got Z against T. Okay. And let's say your initial position isn't at the surface. Let's say the initial position of the air parcel is right here at 2 kilometers. So you're sitting at 2 kilometers. What pressure are you at? 850 is 1, you're probably at about the 800 millibar level, somewhere around there. Okay. And you're looking at an air parcel, right? And you're trying to determine, is that part of the atmosphere stable or not? Is that parcel likely to go up, stay there, or go back out towards the surface, right? So here's the initial position, okay? And the red line here is the environmental lapse rate. The red line is the sounding, the GLR, right? That's actually what the environment looks like. So at the initial position here, here's your parcel. If, and if everyone can follow this, then you're good. If your parcel is unsaturated, it's going to rise and cool at the dry adiabatic lapse rate. That makes sense? If your parcel's dry, is it stable or unstable? Who said stable? Why? Exactly right. Why is it stable? If your parcel's here, right, and Ava's sitting there at 2 kilometers up, and Audrey says, hey, Ava, give it a bump. What does it do? And it starts doing that. It's what? The temperature in the parcel is less, right, than the temperature of the sounding. Everybody see that? It's colder. So in fact, that if you took your hands off it, that parcel would just do this. And come back here. If it's dry. But if you were at the LCL or beyond that, and you were starting to see clouds, it would rise and cool at the saturated adiabatic lapse rate. Okay, in which case it would cool along this line, and at this height, Audrey shouts it over and says, yeah, what's going on here? Is it going to keep going and you take your hands off it? The temperature here is warmer than the sounding, and it'll keep rising and it'll keep rising. So that's why we call it conditionally unstable. It is unstable on condition that you've brought that air parcel to its dew point, that you've got it to saturation. And obviously at about 800 millibars or about 2 kilometers, you're probably there, right? Unless you're sitting above the desert, you're probably not there. But for most part, you're probably there. Does that sort of make sense? So we've got neutral, very rare, but it does happen in very specific locations. We've got stable, right? Under a big fat high pressure where the air is sinking, it's probably stable conditions, okay? So that's not conducive to vertical movement. Unstable, as long as it's dry, it'll cool along the dry adiabatic lapse rate, right? And if it's wet, it'll cool along the saturated lapse rate. And the stability really comes down to, has it reached saturation or not? And if it's reached saturation, it'll continue to cool at the saturated adiabatic lapse rate. Conditional instability. All good. Okay. So here's an example. How are we doing? Doing well. Here's an example of what sounding actually looks like. So you're not going to just see an atmospheric sounding or an environmental lapse rate that's a straight line, right? It's going to change as you go up with height. So here is the environmental lapse rate, this black line here. Okay, yeah, it's wiggling around and up it goes. There's altitude and there's temperature. So that's the vertical sounding that the data comes back from your weather balloon, that solid black line. And you go to the parcel at parcel A, right? And parcel A, if it is sitting at 100% saturation, it would cool at the curved saturated rate. But let's say this is only 50% relative humidity. It's fairly dry at the surface, okay? It will begin to rise and cool at the dry adiabatic lapse rate along the straight line. Make sense? And it'll keep cooling along that dashed line. And if it stays unsaturated, and it stays unsaturated, it will stop right there. If it stays unsaturated, it'll just keep cooling at the dry rate, because here the temperature is always warmer than the surrounding sounding. And at this point, they touch each other and it becomes neutral. And your bubble stops. No more vertical rise. But if along that rise, it reaches its dew point at B, it's on the saturation vapor pressure curve. Now it'll start rising and it'll cool at what rate? It starts cooling at the moist rate, 0.6 degrees per 100 meters, and it follows the moist adiabatic lapse rate. And all along that ascent, it stays unstable because the temperature here, whether it's dry or whether it's moist, is always warmer than the sounding. Does that make sense? Okay. If your sounding looked like this, here's your air temperature, and it did that, and then it did that, and then it did that. That was your environmental lapse rate. You would be in an absolutely stable environment because it wouldn't matter if you try to force it up and cool it at the dry rate or get it to the saturated rate. Its temperature is always way cooler than the surrounding. So here's an important concept. The most stable environment you can have is when your temperature increases with height. And that's known as, anybody know? When your temperature is increasing with height, it's called an inversion, right? It's an inversion. It's an inverse of the norm. That becomes super critical when we start talking about severe weather and tornadoes later on, and your atmospheric sound, okay? So when your temperature increases with height, it's known as an inversion, and it's the inverse of the norm. That makes sense? Okay. Whew. We're throwing stuff at you here. We're nearly there. So let me show you the next one. Oh, yay. I love this. And then we're going to go and look at the live one outside. Okay. Again, so this looks like a complete mess. This is what you're going to take home and spend your entire spring break focused on. Clearly, right? It's going to be your vertical sounding exercise. Yeah. And I think we talked at the start of class about a SQT diagram. We're not going to use SQTs. We're going to use thermodiagrams. So this is a thermodiagram. I'm going to spend a whole lecture on the thermodiagram. And as I said, I'm going to walk you through an example on how to do your take home because it can be a little bamboozling. But let me show you what we're looking at here. So we're looking at mandatory pressure levels, okay, in millibars. So that's the horizontal lines going there. And the vertical lines of temperature, right, in degrees Celsius. So we've got temperature doing that and pressure doing that. In black here, they've put the actual height at which the mandatory pressure level occurs. So here's 500 millibars, and it's at 58. Oh, there's a nice exam question. So here's 500 millibars, and the height is 5,810 meters. Where do you think you are on the planet? At that height. Poles, mid-latitudes, tropics. Is it warm, tall columns of warm air or short columns of cold air? If your 500 millibar surface is at 5,800 meters. It's a tall column of warm air, absolutely. Remember the difference in 500 millibars, that one curve that I showed you, about 5,800 meters to 5,200 meters. And the giveaway is, this is from FWD. So this is from Fort Worth, Texas. Okay, so this is a sounding from Fort Worth, right? You can write from DFW, actually. So we've got temperature and pressure and the heights. The green lines, and I'll just give you the overall setting. We're going to come back and really unpack this later. The green lines are the dry adiabats. Straight lines, right? So these are the dry adiabatic lines. Okay. The blue dashed lines, these guys, the blue dashed lines are the saturated adiabats. Look at this one here, saturated adiabats. Right, so that's the moist adiabatic lapse rate. And then we've got the brown lines that come in, and the brown lines that you can see along the bottom scale, the brown lines is the specific humidity in how many grams per kilogram of moisture. Don't worry about that right now. Okay. What I want you to do is just look at these two lines, the black line. So this is the environmental lapse rate, and I'll stop there. And this line here is the dew point. And that's what you'll see on the sounding. And actually, that's the data that you'll be plotting. That's all you'll be plotting is the temperature and the dew point. And then you've got the wind barbs here in terms of direction and speed. Okay. So what the balloon has done is it's come back and said the temperature here, if you just extended that down, the temperature here is about 30 degrees Celsius, and the dew point is probably at about 18. Okay, so the air is quite relatively dry-ish. They touch here. Hello, what does that mean? Fully saturated. The atmosphere right at this point is fully saturated. Relative humidity of. And then what happens? Then we have an inversion. The temperature increases with height. And look what the dew point does. The dew point completely collapses over to the left. What does that mean? If the dew point here goes from, let's say it's 14 degrees Celsius to, you're less than 100 meters up, and now we're at -10. What's the dew point tell you? It's the actual amount of moisture in the air, right? So when the dew point diverges dramatically from the temperature, you've got a big wedge of extremely dry air sitting in there. Bless you, okay? So that's what a vertical sounding looks like. And what we do in terms of stability is we then plot out what the parcels do relative to those lines. We won't take it any further there on this diagram. I just wanted to show you what a sounding looks like. Okay, and actually, let's see if this works. Let's see what the sounding this morning looks like. Let me. There we go. Just give me 1 second. Google Chrome. Here we go. Okay. So here's the vertical sounding. It turns out the University of Wyoming is where we see the vertical sounding. This is the vertical sounding from this morning for work. And it's probably 60. Yeah, so this is 00Z 26th of February. That's midnight Greenwich Mean Time. Last night. I don't think they've updated. No, they haven't updated. Let me just see if there's a more recent one here. Giftstube, Fort Worth. No, they haven't updated. So this is 6 p.m. last night, right? And here's the temperature, and there's the dew point. Right? We've got an inversion there, but the temperature and the dew point are pretty far away from one another. Okay, the air is pretty dry. That's what you're going to work with on your take-home exercise. Okay, let's just go back to the slides here for a second. So, in summary, when it comes to stability, okay, these are the key characteristics of stable versus unstable air, right? So stable air, slow temperature with height, a very slow decrease or incredibly slight increase in temperature with height. In other words, things are very quiet. Unstable air, rapid decrease with temperature with height change. Has to be. Okay. Stable air, lack of surface warming, suppression of rising motions, may even cause sinking motion. Any kind of stable air is an environment that is not conducive to rising motion. Unstable air, totally different, right? Much more conducive to rising air. You don't have to scribble those all down and learn that all by heart. That's just a kind of general snapshot. So when we then look at how we change stability, got a couple more slides and then we'll end. How do we change stability, right? One of the ways to change stability is through radiational cooling at night, okay? So when the sun goes down, especially on a clear night, and the earth cools more rapidly, right? And especially if you don't have clouds in the air, exam 1, question 17, okay? So you don't have clouds, you've got a clear air night. What happens is the ground cools quickly and the air in contact with the ground cools quickly. So you've got cool air at the ground and relatively warm air above it, right? That's known as a nocturnal inversion. It's an inversion that occurs at nighttime. Okay? So your sounding might look like this. The temperature might increase with height, and then it decreases with height when you get to an elevation that's outside of the inversion. That's very common on cold evenings, okay? Especially in winter. through radiation or cool. And you can see that even if it was moist or dry, it wouldn't matter. Your temperature would be much colder than the sounding, and that would be a super stable environment. Any inversion is the most stable environment. Okay? The radiational cooling is one way to change stability. Okay. Here's the other, heating the ground, right? Any kind of surface heating will increase stability. A little bit of a strange diagram, but let me just explain what we're looking at. We've got height here and temperature, same deal. I just drew this out myself. The green line is the environmental lapse rate. Keep it simple. That's what the sounding looks like. Okay. And your parcel will rise along the dry adiabatic lapse rate here, get to a certain height. If it's dry, it's going to be stable because the air is cooler than the environment, right? If that's the situation right now, let's say that's what the environmental lapse rate looked like, it would be a stable environment. Because if you would cause that parcel of air to rise, it would always be cooler than the environment. But what happens, especially in spring and summer afternoons, is the ground heats up, okay? I think it's going to get to 82 degrees today. So what happens to the surface? The ground heats up quickly to this temperature here. And then what happens? Your air will rise at the dry adiabatic lapse rate, which is now warmer than the environment. So surface heating changes stability. Surface heating makes the air more unstable, right? Because it shifts the temperature dynamics of the parcel to the right of the environment. Okay, and especially if that rising air can reach its dew point along the ascent, lifting condensation level, it will then cool at the moist adiabatic lapse rate, and you'll have stability through depth if you can heat the ground quickly enough.
So when at night we cool the ground, it's stable.
It makes it stable.
Okay.
Because when you cool the ground, so think, I don't know if you've ever experienced this, but if you drive through any kind of valley or topographic low at night, especially in winter, you'll be driving. I noticed this actually when I'm driving. I used to live on West 7th Street and I'd come into the university in the evening sometimes, and I'd come up, West 7th, lots of urban buildings, it would be warmer, and then I'd turn onto university and go down that little seep past the Botanic Gardens, and it gets noticeably cooler there because there's a pool of cool air there at night. So as the ground cools at night, the air in contact with it cools, and that becomes more dense and collects in valley bottoms. And then you have cool air below, warm air above. Okay, you've got a temperature inversion. So heating the ground destabilizes the ground for sure. Here's another way you can change stability, and this happens a lot in the atmosphere, is that you can cool the upper atmosphere, right? Cooling the upper atmosphere changes the troposphere. It destabilizes the troposphere. If you can bring cool air in, because let's say this is your initial level of the parcel here, okay, and your initial sounding looks like this. So here's a parcel, we're at 3 kilometers, and we've got a very, very gentle inversion and then very little change with temperature with height, right? And it would, let's say you're already at the lifting condensation level or beyond it, so you're in the cloud here, your parcel is going to cool at the saturated rate. It's cooler than the surrounding environment. So this is going to be stable unless you cool the entire atmosphere. And this is what the sounding would look like after that. So you force cold air in, and now your parcel will cool at the saturated rate, and it'll be warmer than the cooler environment, right? So you can either heat the ground, which destabilizes the lower atmosphere, or you can cool the middle atmosphere, and that destabilizes the atmosphere. And that actually happens both. Both of those happen in the atmosphere. Okay. Second last slide. I know I haven't given you a break and there's a lot coming at you here. Okay. So how do inversions occur? Okay? Inversions are truly important. They can occur at the surface through radiation or cooling, right? We've already said that. Ground cools quickly, the cold air pools, you've got warmer air aloft. This wedge of warm air is an inversion. Okay. You'll see when we talk about severe weather and tornadoes, there's a specific mechanism for getting dry air in here to this part of the world, and we'll come back to that. But here's another way of causing an inversion. Okay? And this happens a lot in winter. It's a subsidence inversion. If you've got a big high pressure over a region, what's the air doing? Going up or going down in a high pressure? Right? The air's going down, it's sinking. And what happens to the temperature of the air as it sinks? It does what? rising air cool or sinking air does what? It warms by compression. Rising air cools by expansion. So in a big high pressure with gently sinking air, it's warming. And that sinking air and the warming air can cause an upper level warming here. It's called a subsidence inversion. Just gently sinking air will cause a subsidence inversion. It's exactly what's happening outside there now. It happened last night. Okay? And that becomes very important for stability and so on. So the summary of all of this, and I'm glad we're finally at this point, okay, is in a simple scenario, let's say we're not bringing in a cold front because that's another issue. But if we just heat the ground, and that ground causes the air temperature to increase, and that causes the density to go down, and that rising air begins to cool by expansion. If you can get it to its dew point, where the temperature equals the dew point, and you're at the lifting condensation level, and you're on the saturation vapor pressure curve, then you're at a relative humidity of 100%. And if you can increase, if you can keep that air rising, it's now cooling at the moist adiabatic lapse rate, right? Which is a suppressed rate, releasing all of this latent heat, warming the atmosphere, increasing vertical motion. The question then is, how do we get precipitation? Right? Because all we've gotten so far is cloud through that depth. It's all we've got. Nothing at the surface. Something else has to happen to actually get precipitation, whether that's slow sleet, freezing rain, rainfall, whatever the case may be. Okay? That is where we go next time. Okay. I will review stability in more, not more detail. I'll review it when we look at the thermodiagram as well. Okay. All right. If you wouldn't mind just putting the exams on the front here, where Sydney's is as you go out. Thanks. Yeah.
Maybe. I don't know.
Video. That's it.
I have a couple